Hello everyone, I am Sarbartha, and today I am going to present our work Sesame, Software Defined Enclaves to Secure ML Inference Accelerators with Multi-Tenant Execution. Machine learning as an application is ubiquitous, and it is operating on our personal data. Image classification uses ML models for tumor identification operating on patients' health data. Recommendation systems use user data to provide relevant ads or movie suggestions on Netflix. Autonomous driving uses proprietary ML models developed by companies like Tesla to detect pedestrian or obstacle detection. Other applications include malware detection used by antivirus software, email filtering, speech recognition for smart home devices like Google Home, and there are many others. In other words, learning applications are either using users' personal information or are themselves valuable IPs that need confidentiality. ML data privacy is required when user personal data is sent to a classifier in the cloud. For instance, a hospital can send sensitive patient data to a well trained open source disease classifier to the cloud. The outcome of the classification and the patient identity should not be exposed to malicious system software through memory confidentiality violation. Moreover, co-executing applications should not get access to private data through on-chip storage resources with buffer overflow or reading stale data. Data confidentiality and isolation enables sensitive data to be serviced with ML as a service setup, which is growing tremendously given the development of ML inference accelerators and their deployment in commercial cloud servers like Amazon F2 and TPU in Google Cloud. Institutions spend millions of dollars and many man and compute hours to train a model performing classification. These models are proprietary and can be deployed in security critical applications. For example, the traffic light detection system in a self driving car streams video from camera and sends it over to a traffic light detector running on a neural processing unit. The NPU can also run other models either concurrently or sequentially along with this critical application. Sparsity of the model is revealed from execution timing attacks, and model structure can be inferred from memory utilization traffic. Since accelerators are used to provide real time inference, the confidentiality of the model needs protection in such accelerators. Hardware enclaves are used to provide isolated execution environment, providing data confidentiality and integrity. System authenticity is established by the client through remote attestation before sending secret data to the cloud. The model can be run in a trusted execution environment like Intel SGX. Bunch of ML privacy work like Mylin from UC Berkeley and Chiron from UT Austin and others uses CPU enclaves, while GPU enclaves are incubated by works like Graviton or Telekin. But there is a dearth of ML accelerator enclaves, given the large number of ML accelerator papers which are published in academics and deployments in industry. The other existing approach is using cryptographic methods like multi-party computation, garbled circuits, or homomorphic encryption to provide data privacy and model confidentiality. These methods are orders of magnitude slower and defeats the whole purpose of using ML accelerators in the first place and are impractical. To sum up, enclaves are great, but CPU enclaves are not designed to handle ML inference due to large secret data footprint and microarchitectural side channel leakage concerns. ML inference accelerators are more performant than CPUs due to hardware structure tailored to a workload. Moreover, the lack of fine-grained hardware control by fixing the threat model at design time, catering to a fixed set of security primitives, is not optimum. The lack of software hardware co-design introduces unacceptable performance overhead in these existing approaches. To create a performant yet secure ML accelerator enclave, we introduce the key ideas of Sesame. The hardware enclave should be able to handle multiple tenants concurrently given the compute capability of cloud machine learning accelerators, further providing side channel protection through private queues, partitioning, and shaping data structures. The software defined threat model is chosen at deployment time instead of fixing it at design time. This enables private input model definition by the user, and if it is operating on shared hardware or solely operating on the entire hardware. The performance security trade offs are tied to the threat model. This requires a cross-stack solution, which we demonstrate on Xilinx FPGA with ResNet and VGG workloads. The compiler performs offline profiling to optimize the usage of hardware data structures. The baseline ML accelerator execution starts with input and model declaration in TensorFlow or MXNet. The compiler passes then perform graph transformations with offline profiling for tile size optimizations and generate the code for the accelerator. The accelerator APIs then load the generated code to the accelerator and also load the input and model into DRAM. Finally, the accelerator hardware, which is deployed on Xilinx Zinc FPGA in our proof of concept setup, executes the inference and returns the output to the user. The ML accelerator is a decoupled access execute design containing a load, compute, and store units controlled with dependency queues. The driver loads the input and model onto the DRAM. The load unit consists of double buffered input scratchpad of size 256 kilobytes and weight scratchpad of 2 megabytes. There is an instruction unit supporting basic load, gem, ALU, and store instructions. The compute unit consists of 16 by 16 gem units and ALUs. The store block again includes accumulation scratchpad and which store local variables and a store scratchpad for routing the result back to the DRAM. Vulnerabilities can be introduced either by a malicious cloud system software or co-executing tenants in such a non-secure setup. Private data confidentiality is a concern as secret data is resident as plain text in DRAM. Data transfer from memory to accelerator suffers from memory read bus utilization snooping by system software. Inside the accelerator, access control violation and buffer overflows introduce unauthorized scratchpad read writes. Further, execution timing attacks reveal model sparsity. Dependency queue tampering provides attackers with widgets to misclassify the secret data. Similar attacks are possible on the output data. The vulnerabilities depend on attackers' visibility, and all of them are not applicable for each threat model. For example, if the accelerator is running a single tenant, the malicious tenant vulnerabilities are not applicable. Also, it only applies to the secret data and also varies with the type of the secret data, whether it's model or input data. Software hardware co-design ensures use case based configuration of hardware security widgets. Offline profiling optimizes tile size and security passes before code generation, and ISA enhancements provide fine grained data movement and zeroization of only the secret data. One of the use cases is private input on public model, which only needs secret input confidentiality, unauthorized scratchpad read-write protection on the input scratchpad, and execution timing attack prevention. The input size is known to the attacker, and and memory bus snooping utilization channel doesn't reveal any information about the input. The other use case is the public input on private model. The input data confidentiality here is not required. We only need the model confidentiality. Deployment time threat model thus helps to provide only the required amount of security, minimizing performance overhead for security we don't need. Sesame ISA extensions provide loading, storing encrypted data through load E and store E instructions over unshaped memory bus. If we need memory traffic shaping, then memory shaped load store transactions are generated through load AC and store AC instructions. Constant time execution is performed with gem underscore c or ALU underscore c instructions, and secret data zeroing is performed using a zeroize instruction. DNN layer can be revealed from the memory bus utilization channel as shown in the figure. Traffic shaper logic provides a constant trace of a predetermined bandwidth by sequencing real transactions into regular intervals and generating fake traffic to hide read-write dependencies. Use after free attacks are possible by malicious co-tenant even after execution completion. So let's say during the execution, we partition our scratchpad so that there is no overlap between multiple tenants, but the malicious co-tenant can still read stale data after execution and violate secret data confidentiality. The zeroize instruction writes zero to scratchpad regions containing secret data and generate local variables from and the generated local variables from secret before reprovisioning the on-chip storage to a different tenant. Let us see how Sesame defenses handle each of these vulnerabilities. For private data confidentiality, the user defines secret variables in high-level code. The compiler generates load underscore e and store underscore c e instructions for encrypted data, which is decrypted by the hardware encryption block. When the user specifies model as secret, memory utilization bus snooping becomes a valid vulnerability, and the memory traffic shaper is activated through configuration registers. The compiler also performs offline profiling for best tile size with memory traffic shaper enabled and also prevents bank conflict by DRAM data placement. Unauthorized scratchpads read writes are prevented through basebound check hardware at each instruction and zeroizer block, which is triggered by each zeroize instructions to clear secret data from scratchpad. Execution timing attacks are thwarted with constant time gem and ALU instructions on secret data generated by compiler through gemc and ALUC instruction. Dependency queue tampering is prevented with partitioned private queue for each tenant. We evaluate Sesame proof of concept on Xilinx Zinc FPGA running at 100 MHz with a dual-core ARM processor running the accelerator driver. The two evaluation modes include temporal and spatial sharing. The temporal sharing, we have a single tenant which is running on the entire accelerator, and the special sharing mode, we have four tenants sharing the accelerator resources, including memory bandwidth. We run end-to-end image classification with variants of VGG, ResNet, and AlexNet trained models, which are taken from MXNet model zoo. There is a 5 to 9% binary size increase due to addition of zeroize instructions. The figure also shows the usage of different flavors of load store instructions in different threat models. In the private input case, which is the second bar, the inputs are loaded with load E instruction. The private model scenario adds load SE instructions to load encrypted model data over shaped memory bus and uses load S instructions for loading inputs. The execution units are constant time when operating on secret data. Next, we talk about the offline profiling of tile size exploration through auto-tuning, which provides the best runtime synergy between data loads and computes. The plot shows a significant runtime variation across different possible tile sizes and exemplifies that state space exploration is a major step in providing the best performance, yet providing the security required for the particular threat model. We further optimize the zeroize security pass by reusing the same scratchpad regions across tiles and zeroizing the scratchpad region only at the last tile of the secret matrix. This results in significant binary size and performance overhead reduction. This is also increase in There is also increase in scratchpad reliability and reduction in the overall power consumption. Finally, we show the overall performance overhead for different threat models, which are evaluated in our setup with either Karma 128 encryption or AES 128 encryption. The baseline assumes no security for either inputs or models. The performance overhead ranges from 3.77 to 25.81% with Karma encryption block and 4.92 to 34.87% with AES encryption decryption. There is an increase in overhead in the private model scenario because it uses private queues and the memory traffic shaping logic is enabled. A further evaluation of a multi-tenant case with four concurrently running tenants sharing equal accelerator resource shows a performance overhead of 3.31 to 12.78% with Karma encryption block and 4.86 to 16.73% overhead with AES. Now we evaluate the effectiveness of the memory traffic shaper. So first, on the naive design, the model boundary is detected with high precision with our classifier models working on memory utilization trace collected during runtime execution. But with memory traffic shaping logic enabled, the classifier was unable to detect any layer boundaries with high precision. Once the layer boundaries are detected in the unshaped trace, we apply a bunch of classifiers which are trained a priori on different tile sizes. Though execution time only classifiers provide all the different types of layers in AlexNet and VGG11, we trained more sophisticated classifiers like SVM, MLP, and CNN based ones with discrete wavelet transform, which gives much more layer type detection accuracy for unshaped memory channel. The shaped memory bus doesn't reveal any the layer types because the layer boundary detection is incorrect. Finally, to conclude, Sesame introduces accelerator enclaves. The introduction of software-defined enclaves will lead to a slowdown scaling with the threat model, and the compiler performs performance and security optimizations. Fine-grained control to hardware resources through ISA extensions for handling encryption, zeroization, and constant time computation as and when required on the secret data is done on Sesame. Enabling and disabling hardware security widgets like memory traffic shaper and private queues and partitions, scratchpad partitions for isolation are also part of the Sesame design. Finally, the Sesame serves as a tool to decouple ML users from providing security guarantees to his machine learning model or data by using a hardware and software co-design approach. Here are some references which we use in this presentation. And finally, thank you for listening. The paper is published at Archive, and the link is there in this slide. And now I'm happy to take questions. Thank you. Bye.